regioselectivity and stereoselectivity in Diels-Alder reactions. In all the examples that we have discussed so far, either the diene or the dienophile was symmetrical. Say for example here, the diene, all of these dienes are symmetrical. But when you start the Diels-Alder reaction with unsymmetrical diene and dienophile, then it's going to lead to two different products. Okay, here are the two different products. You can see here, both of these, diene and as well as the dienophile, are unsymmetrical, and therefore it resulted in two different products. But only one of this is going to be a major product. Let's find out which one would be the major product. First, why two different products are obtained? Because the reactants can be aligned in two different ways. Okay, so here are the two reactants. This is the diene and this is the dienophile. And we are going to keep the dienophile's orientation constant. Okay, so in both of these. And we are going to switch the orientation of the diene. So the diene can be like this, where the OCH3 is pointing up. Here it's upside down. Okay. If the reactants are aligned in this way, then this is the product that is obtained. This is a 1,2 product, okay, where the two substituents in the adjacent positions. Whereas the reactants, if they are aligned in this way, then it's going to result in 1,3 product. But which of these two products will be obtained? For that, we have to look into the resonance contributors of the diene and as well as the dienophile. In the diene, we do have an electron donating group. So this OCH3 group is an electron donating group, which means these electrons that is present on oxygen is going to be donated here. So it can form this resonance contributor where you can see that this carbon is going to have a partial negative charge, right? So let's draw the resonance contributor here. In the same way, if we draw the resonance contributor for dienophile, this is an aldehyde group, which means it's going to withdraw the electrons. This oxygen is going to withdraw the electrons. The electron shift is in this direction, right? And therefore, this carbon will have a partial positive charge. Now, when you want the product to be formed, you want the negative charge of the diene to come in contact with the positive charge of the dienophile. So basically, these two ends need to come together, and therefore, these two carbons also need to come together to form the cyclic structure, right? And when you form the cyclic structure, you can clearly see that the two substituents, the OCH3 and as well as the aldehyde functional group, are in the 1,2 position with respect to each other, right? So this is going to lead to the 1,2 product. Now let's see what's going to happen if you're going to switch the diene. So here the diene has been switched. So let's again draw the resonance contributor for this. Now if you want this 1,3 product to be formed, you want this negatively charged carbon to come in contact with this carbon of the dienophile. But this is not going to happen because this carbon is not even positive. So when you look into the resonance contributor, it doesn't even have a positive charge. So it's not going to happen. So in Diels-Alder reaction, 1,3 product is not going to be observed. So you only get the 1,2 product. And because one product is formed preferentially over the other, the Diels-Alder reaction is a regioselective reaction. In order for the Diels-Alder reaction to take place, we want the conjugated diene to be in the s-Cis conformation. Now, what is this s-Cis conformation? A conjugated diene such as 1,3-butadiene is more stable when it's in the planar conformation. But there are two planar conformations. One is the s-Cis and the other one is the s-trans. Here are the s-Cis and s-trans conformations of butadiene. When you say s-Cis, the two double bonds that is present in the butadiene are cis with respect to the single bond. And in the s-trans, they are in trans position with respect to each other about the single bond. The s-trans conformation is slightly more stable compared to the s-Cis conformation because these two hydrogens are going to have some steric strain in the molecule. If the conjugated diene is an s-trans conformation, then these two carbons are far away from each other and therefore they cannot undergo Diels-Alder reaction unless they rotate about the carbon-carbon single bond. Compounds such as this 1,3-butadiene can rapidly interconvert between s-trans conformation and s-Cis conformation where they can rotate about this single bond because the energy difference between the s-trans conformation and the s-Cis conformation is very small. Because of this interconversion and its ability to exist in s-Cis conformation, 1,3-butadiene can undergo Diels-Alder reaction. But a compound such as this, which is locked in the s-trans conformation, cannot undergo Diels-Alder reaction because there is no rotation about the carbon-carbon single bond because of the cyclic structure. So this is s-trans locked and therefore it cannot undergo Diels-Alder reaction. Conjugated diene that is locked in the s-Cis conformation, such as what we see in this case. Okay, so here we have the two double bonds which are cis to each other above the single bond. Okay, so this is locked in the s-Cis conformation, and therefore this is going to be very reactive in a Diels-Alder reaction. Since you're starting with a cyclic diene, this is going to result in a bridged bicyclic compound, but you're going to get two different products, and out of this, one will be a major product. Whenever Diels-Alder reaction creates an asymmetric center, then the product will be a racemic mixture. Here is an example. Here there is a new asymmetric center that is created, and therefore this is definitely going to result in a racemic mixture. The Diels-Alder reaction is an example for syn addition, where one phase of the diene adds to one phase of the dienophile. So if the substituents in the dienophile are cis to each other, the product will also have their substituents cis to each other. Okay. So here is a trans dienophile where the two substituents are in opposite direction. So in the products also they will be in the opposite directions. So these are the trans products that are obtained. And because this reaction is resulting in two asymmetric centers, a pair of enantiomers will be obtained.